So what can isometries do? If I have a transformation that preserves the distance between 2 points, what does that constrain? How does that constrain my transformation to be something in particular? So we're going to look at 3 examples today, and your task between now and Monday is going to be with the other members of your team to come up with a proof for why each of these examples does in fact qualify as an isometry according to the definition of isometry. The first example are translations. So in a translation, the way I think of it is we just take our piece of paper that has a figure on it, and we just slide that piece of paper on our table without turning it, without flipping it, just by moving it, just by changing the location of a figure within the plane. We get something called a translation. And we get different translations if we move the paper in a different direction or if we move the paper a different amount of distance, right? And so it takes, in order to define a given translation, we need to specify how we're translating. And in linear algebra as well as in multivariable calculus, we'll typically do that by fixing a vector, v, fixing a point inside the xy plane, and saying, well, we're going to define a translation by taking that vector v and adding it in to all of the points x in the xy plane, just by adding t of x equals x plus v. That's going to take every point x and it's going to move it a v vector away from where it used to be. Right? So that's algebraically in linear algebra and multivariable calculus, that's how you define a translation. So we can write that out in coordinates. But in our world, we don't have a coordinate system. We want to do geometry that is coordinate-free, which has a lot of benefits. Right? One of the benefits, as we'll see a little bit later on, is that being coordinate-free tends to make things simpler. We have to think a little bit more abstractly about them sometimes, but we don't have to wrestle with some really complicated formulas for how to do things. We're going to look at rotations and reflections. The formulas for those are kind of nasty in coordinates, but we can understand them just using the foundations of geometry in a more elegant way that makes it easier to do proofs, for example. And so what we have to try to figure out is how do we define what it means to translate the plane in such a way that doesn't involve us using coordinates the way we did in linear algebra. And so the way that we do it is, since we don't have vectors at our disposal, we'll replace that vector with a line segment, AB. Right? And we're going to define the translation of the plane defined by that segment AB as that transformation for which, for every point P, and then here would be its image point P prime, right, that I need the line segment from P to P prime. Well, what should the relationship of that line segment to AB be? So we have to have the same shape in our image as we had in the pre-image. And what should the relationship of P prime and AB be? Okay, so they need to be the same length, so they need to be congruent segments. What else? Parallel. Sort of written into the DNA of a translation is this idea of parallelism. So AB and PP prime should be 2 parallel congruent segments. Where else have we heard parallel and congruent in our course up until this point? One pair of parallel and congruent segments. It defines for us a parallelogram according to theorem 2.3.5, I want to say. I always get that citation wrong, so I'm going to want to double check that. But yeah, that's how we're going to understand what it means to be a translation, is that it's a translation according to the line segment AB if AB, P prime P, forms a parallelogram. Right? So that's how in a coordinate-free way we're going to define what a translation means. So we don't have to know anything about vectors. We don't have to do any vector arithmetic. We don't have to even have a coordinate system at our disposal. All we have to know is what is a parallelogram. So that's how we're going to define translation. And it turns out, this is not trivial either. This is something that we should probably talk more about. But it turns out that the translation defined in such a way by a segment AB is unique. So if I tell you we're going to talk about the translation that moves the point A to the point B, there's only one translation that does that. And so we'll use the notation TAB as our authors do, to define the unique translation which moves the point A onto the point B. And then by extension, it moves every other point of the plane to a point which makes a parallel congruent segment with AB.